All right, we're back. Let's see. Are all these people here? They're here, right? Yeah, I can see. All right. Let's see, my clock says 1:20. All right. So now what we're going to do, we're going to talk about, whoops. We're going to talk about allele sharing. And I don't know, I know Joan likes my presentation of this. We'll see if you like it. We have plenty of time, so stop me if you don't understand anything. All right, we're going to talk about descent graphs. And this is a particular pedigree, and there's one particular descent graph you can see corresponding to this pedigree. What you have to remember is that the maternal allele is to the left and the paternal allele is to the right. And the only way I can remember that is that M becomes before P in the alphabet and L for left comes before R for right in the alphabet. But once you know that, you're in shape. Now, this is a maternal allele. It comes from some mother up there. This is a paternal one. This is a maternal one, maternal, paternal, maternal, paternal. It is assumed that all these individuals are independent. If they're not, you haven't got far enough back. Now, you got to remember, we don't have to have the right descent graph. We're going to sum over all possibilities. So this is just one possibility. And what this says is this allele comes from this individual, and that's maternal. From here, that's maternal. So this is a grand maternal allele. This one is also a grand maternal allele. This one, however, is a grand paternal allele. This one also comes from this. It's a grand paternal allele. This one is a grand maternal allele. This one is a grand paternal allele. This one is a grand maternal allele. And this one is a grand paternal allele. And similarly, this one is a grand paternal allele. Yeah, comes from there. This one is, I got it right. This one is a grand maternal allele. This one is a grand paternal allele. And this one is a grand paternal allele. I think I got them all right. Okay. If I haven't, shout out and let's get it right. Okay, everybody agrees, I hope. So now we're going to talk about how we calculate identity by descent from a descent graph. So given a descent graph, the number of alleles shared identical by descent is equal to the number of common founder alleles. All right. Here we have, let us look whoops, sorry. Let us look at examples. Individuals 1 and 2. 1 and 2, they share no alleles identical by descent because they're both founders, and by assumption, all the founders are independent. 1 and 5. Let's look at 1 and 5. They share one founder allele. This one. 1 and 6. Here's 1 and 6. They also share one founder allele. This one. 5 and 6. It says 0. Let's look at that. 5 and 6. 5 and 6. They don't. These two alleles come from a different. They don't share any founder alleles identical by descent, so it's 0. 7 and 8. Look at 7 and 8. they share this one and this one. They also share, or at 7 and 8. They share, whoops, am I at 7 and 8? Sorry. They share this one and they share this one. So they share 2 alleles identical by descent. 9 and 10, how many founder alleles do they have? They have just this one identical. And this one comes somewhere else. 9 and 5, they don't share any alleles identical by descent. Nope, they don't. 9 and 8 share 1. 9 and 8, yes, they've got this one allele, founder allele, identical. So now, given the descent graph, remember the number of alleles shared identical by descent is equal to the number of common founder alleles. Inheritance vectors. So an inheritance vector is another representation of a descent graph. So it's telling us the descent graph. That's what it is. But instead of looking at the descent graph, we just have an inheritance vector. An inheritance vector for a given locus is a string of bits. And we're going to that represent each allele that each of n pedigree non-founders had. So there are n pedigree non-founders, and therefore there are 2n bits. Okay, here we have, remember now, we're going to have a, well, let's look at it. This will be easier, I think. Bij is going to be 0 if the common corresponding allele is grandmaternal, and it's going to be 1 if it's grandpaternal. So that's what we have to know. So let's look back at this. Okay. Let's see. Here we see this is maternal, so it's 0. This one is also grandmaternal from up here, it's 0. This one is grandpaternal, it's 1. This one is also grandpaternal, it's 1. This one is grandmaternal from here up here, so it's 0. This one is grandpaternal, so it's 1. This one is going to be grandmaternal. There's the grandmother up there somewhere. It's 0. This is going to be grandpaternal, comes from this grandfather, and this is 1. Okay. Let's do a little bit further. Let's see if I can do it without seeing the answer. So let me see. This one is grandpaternal. It'll be a 1. This one is grandpaternal. It'll be a 1. This one is grandmaternal. It should be a 0. This one is grandpaternal. It should be a 1. This one is grandmaternal. Should be a 0. This one is grandpaternal. Should be a 1. Let's see if we've got that right. Yep, we got it right. That's what I said. All right. Whoops. So let us consider an inheritance the inheritance vector probabilities for one autosomal locus. All right. This is what we have. First of all, the probability of the marker data and B, whatever B is 0 or 1, it's the probability of the genotypes, the markers, and the inheritance vector value for all those genotypes G, B, M, where that is the set of G consistent with B and the marker data M. bit like being in the pheno set, if you like. So M is the vector of marker phenotypes, MJ, one for each pedigree member. B is the inheritance vector. G is a vector of genotypes, one for each pedigree member, and this is the set of all G consistent with B and the marker data M. All right. So let F be the set of founders, N the set of non-founders. Then, and let this be the population frequency of genotype GJ. Then PMJ given PGJ is the probability of marker phenotype MJ given genotype J. It's the penetrance. This is the penetrance. Then this particular value here is just for all founders. It's the probability of the founder genotype times the penetrance, the probability of the marker given the founder genotype. And then you have to product over all the non-founders here, and you have 1/4. 1/4 is a transition probability. Every allele is transmitted one property 1/4 times the penetrance, the marker, I can't see where my arrow is, the marker of phenotype given the marker genotype. All right. So that's all we have to do, really. As long as we know these founder probability values and we know the penetrance here and we know these values here, we get there. We first of all get this and we sum it over all genotypes that are consistent with a genotype. So, sorry, for all possible G consistent with the B and the marker data. That's what I meant to say. All right. So how do we calculate? Let's take a very, very simple example. All right. This is a genotype, but it's an ordered genotype. B/C is not the same as C/B. We know that B is maternal and C is grandmaternal, grandpaternal. We know that. I mean, not for a founder, but in general. So this is what we're going to look at. We're going to look at this simple example of 2 parents and 2 offspring. We're going to assume that all allele frequencies in the population are 1/3. No matter what genotype you've got, whether it's B/C or ordered genotype or A/A, they're all going to be 1/9. All right, that's easy. Everything up here is going to be 1/9 in the founders. All penetrances will be 1 or 0, so the probability of the genotype being BC, given you've got the ordered genotype BC, will be 1. It's just, we're going to assume everything is simple. Then it turns out that this probability of GMB is given B is 0, 0, 1, 1, 0 grand maternal, 1 grand paternal, is going to be the population probability of B/C times the penetrance. Here I've put in A/A. It doesn't matter. I can put anything here because we're assuming we know what's in here. We don't know, but I'm just going to put, and it's not going to matter in this example because we're going to assume all these things are equal. Whoops, excuse me. And then you've got 1/4 for the AC given AC. And wait a minute, I've got a quarter AB given AB, a quarter that. So what it's going to be 1/9 by 1/9. Remember, we've assumed all these genotype frequencies are the same. Quarter, quarter, and it's going to be, it turns out to be 1/1296 if you put all this together with the complete penetrances and given allele frequencies. So this is what it turns out to be. Okay, now what you have to realize is at this point we standardize all these likelihoods, if you like, these and so once you divide by the sum of them, what you have is this likelihood vector for the previous nuclear family. Whoops, there. So the probability of the data given B equals 0, the bits are 0, 0, 1, 1 for the SIBs is this, and the likelihood is proportional to that. In other words, we get all these 16 of them, and we sum them and divide by the sum, and we find that this one is going to be this value here. So we have 2 to the 2n 16 bits, or if you like, series of 4 bits. We have 4 inheritance vector bits, 2 to the 2n minus f. N is the number of non-founders, f is the number of founders. Now, this is what we notice. If we look carefully here, we see these 4 numbers here. They're exactly the same as these 4 numbers here, but in a different order. And again, these 4 the same again, but in a different order. These 4 again, but in a different order. So, and this will always be true. So we only have to calculate one block. And once we've done one block, we've done all the blocks. Yeah. So that's the point. So 2-point likelihoods. Now, any questions so far? I hope this is clear, because if it's not, you may as well forget the rest. No questions? All right. So the inheritance vectors change from marker to marker along the chromosome. That's what happens. That B, that vector of B bits changes from marker to marker. Each change from grandpaternal to grandmaternal, grandmaternal to grandpaternal implies a recombination. And remember that we have to have 3 generations to know anything about whether a recombination has occurred. And so to get at the recombination fraction. Because, as you remember from, if you only have SIBs, you may find a value, but it could be that same value complemented. You don't know. It could be the other side of a half. Mind you, it tends to be such a small value, or usually, that you can assume that it is close to 0 rather than close to 1. But that is an assumption. Between each pair of matrix markers, we have a transition matrix T is created, such that this T is the recombination fraction times this here is the number of bits that differ between B1 and B2, okay? Number for the first locus, grandmater, we've got the one from the first locus and on the second locus over here. It's theta, the D times that times 1 minus theta times 2n minus this, because there are 2n all told. These are the inheritance vectors, and this is the number of bits that differ between B1 and B2, and theta is the recombination fraction between the 2 loci. So this is a transition matrix going from one set of bits to another. All right. So a 2-point likelihood is given by this, which is a quadratic form of this matrix in these vectors. So this is the 1 by n element likelihood for marker 1, and they transition to this L2 is the n by 1 element likelihood vector for marker 2. And this is the transition matrix between markers 1 and 2, and capital N is 2 to the 2n, where n is the number of non-founders. So if you remember, think of this as L prime. This is a certain length. This is a symmetric matrix. Well, it is in this case anyway. And then this is the other vector, which is now, this is a row vector, a square matrix, a column vector. So this turns out to be a scalar. It's a quadratic form. In other words, what we're saying is, if you look at this carefully, what we're doing is summing over the bits at marker 1, the bits at marker 1, the bits at marker 2, the likelihood marker 1 given B1 times the transition going from one to the other, and times the likelihood for marker 2 at B2. That's exactly what this is. It's a scalar at the end. Okay, it's a quadratic form scalar. It's the quadratic form of this matrix in these in the elements of this vector here. Multipoint likelihoods, which I think we probably went over before, but now we can see what's going on perhaps a little better. It uses the joint information from 2 or more markers in a chromosomal region. It can be used to place a disease locus on an existing marker map. Each analysis assumes a particular locus order. You get your locus order wrong and you have problems. So you have to have the order correct. And by using multipoint, you increase the information at each point along the chromosome by using information from other points along the chromosome. That's the whole point of multipoint, is to be able to use the extra information. So the multipoint likelihood for M-linked markers on a chromosome is given this way. It's the likelihood for the theta, and here you have the first marker, you have this diagonal transmission, and then you have between the first and the second, and then you have you go on, keep doing it. The ith term is, the ith is just this transmission from I-1 to j, Li, I to I plus 1, Li plus 1, and you go right along the chromosome till you get to the last one. This is again a vector. This is a square matrix, and this is a vector. You can see that probably better when I give you, that's an m by 1 vector of recombination fractions, theta I plus 1, between markers I and I plus 1, going from I equal 1 to marker 1. Okay. This one is an n by 1 element likelihood vector for marker I, and you keep having them all in here. And lastly, Li is the n by n diagonal matrix with diagonal elements equal to the elements of Li. All right. So this is the transition matrix between the markers I and I plus 1. Now, this is all described in this paper by Haseman-Elston. It's a neat trick. It's a divide and conquer method. It's fast, and yet you can even let the recombination fraction or depend on covariates quite easily. What I want to tell you about this paper, though, if you look at it, unfortunately, if you look at it on the second page at the top of the second column, the words grandmother and grandfather are unfortunately interchanged, and that will confuse you. I don't know how it happened, but if you'll remember that, you've got to cross out grandmother, put grandfather, cross out grandfather and put grandmother, then it will all make sense. I'm sorry about that. but I think you'll find this paper interesting to read. Well, before I go on, any questions about that? I say this is more in spirit, I suppose, to the Landau-Krugliak algebra, but it's not that. It's a much better one because you can make the meiosis specific on anything you want, and it virtually doesn't take any longer. That's all explained in the paper. Okay, it's a divide and conquer method, and it goes very, very fast. No questions? Well, we're going like a house on fire. We're going to finish very early if there's no questions. I'm just warning you. All right. Let's talk about model-free sibling pair linkage analysis. We're going to talk about regression tests and mean tests, both of which are available in SibPal. Just for simplicity, let's look at a simple example. Let us assume the trait with only additive genetic variance. Okay. Now, remember, we're estimating quantitatives relative to our sample and not the population. We're going to assume the pairs are independent, but we'll find out something else in a minute. We'll specify what we're really assuming in a minute. We assume the population is at pan-mictic equilibrium, all mixed up, Hardy-Weinberg proportions, all at equilibrium, and no selection, no immigration, no, just, and let us suppose we have a sample of n independent SIB pairs. Just make it easy to start off with, n independent SIB pairs. Then, let Xij be the trait value of the, let's see, have I got it down here? Well, let me see, is it it's the ith pair. Yeah, we get it. The jth, the ith member of the jth pair, ith member of the jth pair, because there are 2 members to a pair and we have n pairs. Okay, so we're assuming that's basically a mean plus some genetic effect plus whatever's left over. So let Yj be the difference between these 2 squared. And that turns out to be here. The mean doesn't come into it. That gets canceled out. Okay. And this is what we have squared. So what do we have? Therefore, Yj is equal to twice the additive genetic variance, we're assuming each of these this, minus the covariance between these 2, plus some residual. Now, this assumes that this difference in environmental effects for a member of the pair is independent of the difference in the genetic effects. That's what we're assuming. Again, for simplicity, assume there's only one linked trait locus at a given point. And what we're doing now is basically going through the Haseman-Elston 1972 paper. Let pi jt be the proportion of alleles shared identical by descent at the trait locus by the jth pair of SIBs. Okay, that's SIBs. So it's at the trait locus. We're assuming we're right there at the trait locus. Then this expected value of y, given the proportion identical alleles shared identical by descent at the trait locus, is just twice the additive genetic variance plus some what's left over, if you like, some residual variance, minus, and this is twice the additive genetic variance, times the proportion of alleles shared identical by descent at the trait locus. This is the main result, one of the main results of the paper, okay, that you can do this. Now, if the trait locus T is linked to a marker locus M with recombination fraction theta, and pi j M is the proportion of alleles shared identical by descent at the marker locus by the J-set pair, then for full sibs and also for half sibs as far as beta goes, this regression, you see, this is, if you like, the regression on pi jt. Now we're going to do the regression on pi jm. We get the expected value of the trait difference squared given this is all this junk here, which is some intercept. And the regression on the proportion at the marker is -2 sigma alpha squared times this 1 minus theta 2 squared. That's the whole point. So that from this regression equation, we can estimate. We can sort of estimate this whole thing. We can estimate beta. Now look at this regression coefficient beta. Okay. If you look at it, it's 0 if and only theta is equal to half, put that goes to 0, or if sigma a squared is 0. So if it's 0, either you're far away or you have no additive genetic variance there, okay, at that point, at the marker. This is because this allows for the fact you're at the marker, not at the trait locus. On the other hand, this is less than 0 if and only theta is a half and there's no additive genetic variance. That's the whole point of the Haseman-Elston regression. This regression coefficient is only, it equals 0 if either you have no additive genetic variance or you're so far away that just recombination fraction, or if you have both a recombination fraction not equal to half and an additive genetic variance there. The not equal to half, you know, the recombination, we're not saying what the recombination fraction is, because you, from these data, it'll be symmetric about a half, but you know it's not a half if you have a negative regression. So now let's look at y. We know that the regression on y is the pi jt, the minus sigma 2 sigma a squared. Now let us look on here we're at the trait. Now let's go and start looking at the marker. This is at the trait locus. At the marker locus, basically it's the same thing, -2 sigma a squared, but it depends on the correlation between the trait and the marker probabilities identical by descent. In fact, what you have here is this 2 times 1 minus theta squared, as we just saw. So suppose we have a pair of sibs whose parents are A1, A2 by A3, A4 at the marker locus, and suppose there's no dominance. Okay. Then the proportion of alleles at the marker locus is a half the number of A alleles the sib share in common. And in general, we can let f hat ij be the probability, given the marker information available, that the jth pair of sibs share I alleles identical by descent at the marker locus. This would be the prior probability based on relationship alone. This with a hat on is what you estimate it to when you've got marker data. Okay? So the mean probability they share an allele identical by descent is the probability they share 2 plus half the probability they share 1. So this is the basis of the mean tests in SIBPAL. Now, for any pair of relatives, we estimate the proportion of values identical by descent at the marker locus by pi hat jm, which is f2 hat 2j, that's a half f1 hat j. In other words, these are basically the proportions as estimated from the regression equation. At the trait locus, as we have just seen, if we take this difference squared, we've just seen that the mu's cancel out. You have some baseline, some regression on the this is the regression coefficient here, and this is an added bit if you have one allele shared identical by descent. And so it turns out to be this. Okay, this is equal to this if you work it out. Whoops, sorry. But now let's look at, this is what we call the difference. It's the original Haseman-Elston. We're just looking at the trait difference between the trait for the two SIBs. Now let's look at the mean corrected sum and square that. This is the mean corrected value for SIB1. And now we, instead of taking a difference, we've got a sum here and we square it. Now the whole point is that we now, if everything is correct, we get just the opposite of this. We have plus this, minus this, plus this, minus this at the trait locus. Okay. But notice this, we cannot calculate it without knowing the mean. That's the problem. The neat thing about the original Haseman-Elston was you didn't need to know the mean. Now you have to know the mean or put something in to be able to get all this. So now if you take what I call the sum minus the difference, you get this, where alpha is a quarter of this baseline here, but this is equal to now at the trait locus. The difference is simply this, and alpha measures all the residual sibling covariance rather, and Gen IBD can be used to estimate the pi hats, the F2 hats at all locations from available marker data. And SIBPAL can be used to perform the regression. Okay, so that's the point. Now we have two different ways we can look at the difference, which was the original Haseman-Elston. We can also put in the sum. But remember, to do the sum, we have to do something about these means here because we don't know what they are. And in fact, okay, let's redefine the difference as minus a half this. And so we have this at the trait locus. Let's look at the sum of this. We have a different baseline, but we have the same thing going on at the end, okay? So let us take as dependent variable now, instead of the original difference, let's take a weighted average of the difference and the sum, okay? The two weights add up to 1. This is the basis for all the refinements of the original Haseman-Elston that have occurred over the years since the Haseman-Elston paper was first published. Okay, we now look at not only the original difference, but also the sum, and we can weight it, get a weighted average. And what we do, we can get p-values can be obtained by sampling the permutation distribution. So now we have to talk about these weights. Okay, what do we get? There are different values of the weights, how we do it. and that leads to different variations, if you like, of the original Haseman-Elston test. First of all, let's consider Sibships that are size greater than 2. All right. In W2, we assume all the YDs and YSJs are independent. The weights are inversely proportional to the residual variances of the 2 regression equations. So they're not independent, but we just assume they are. But remember, you can use whatever method different methods available, but the best is to use the permutation. You can use a sandwich estimator that's available, but better is to just use permutation. W3 allows for the correlation between the YDJs within a Sibship and among the YSJs within a Sibship, so that you don't have to have independence of Sibship pairs. W4 allows for the correlation of the pairs of YD and the YS within a Sibship, non-independent of sum and difference. And what happens is, as you go from the original Haseman-Elston to Y2, to W2, to W3, to W4, you make additional assumptions and you get more power. So this is to say, fine, why don't we always use W4? Well, the problem with that is you may start having, well, you may get problems and you may get instability, as I think we saw. So what you do typically is, if you're not doing the original Haseman-Elston, you start with W4. If you get reasonable answers, you stop there. If they're actually highly unstable because you're estimating too much, you go down to W3. And if it's still like that, you go down to W2. And you may have to go to the original Haseman-Elston. Though, I say, usually one of these will work quite well. This one, well, it's the most powerful when it works. That's the problem, when it works. Now, this is some graphs in a paper by Sinha and Gray-McGuire. You remember the difference does not depend on the sample mean. Otherwise, you have to get an estimate of the sample mean, and one of the options, perhaps the best option, is to use the BLUP, the best linear unbiased predictor. But when samples are highly ascertained, then what this paper shows is, according to what percentage is ascertained and things like that, what it says is that you are better using the mean. If you know it, use the mean from the population rather than try and estimate, which in this paper is called the BLUP PM, BLUP population mean. That's a peculiar notation, but that's what they did. I'm not going to go through these graphs in detail. You can see how you can sometimes get more power. Whoops. If they're all linked, if all the pairs are linked, then you get quite a bit more. If it's, let me see, this is unlinked. This doesn't make sense. Oh, it's dominant or recessive, and sometimes you get more power. But my take-home message from this paper is I would always use the BLUP. And there you've got different lines, which you can't always see for W2, W3. W3 and W4 overlap, and so you can't see them. And you can see here the denotes the population mean when you use it. Anyway, I personally don't think this paper is very helpful. This slide is there because once upon a time, I can't think of her first name, Gray-McGuire, what was her first name? I can't think of it. Someone will think of it. She put those in. What's her name? Tell me. Somebody. Courtney. That's right, Courtney. Courtney Gray-McGuire was presenting this and she put these slides in, but quite frankly, I don't think they're very helpful. Okay, now you can use general estimating equations if you want. That's all available. That allows for the correlation structure between the pairs. Full pair of SIBs says 0, 1, or 2 SIBs. And you can estimate the correlation separately for sums and differences for pairs of pairs sharing 0 or 1 SIBs and with or without the pi hat in the model. You can permute the values of pi hat to obtain empirical values. I think that's the best way, especially if you have full marker informativity. All right. It seems to me we're coming up to the break fairly fast. So no questions? I don't know. What is the time? Oh, we start again. Yeah. So we got plenty of time for questions if you want any. So I'm going to compare now the Haseman-Elston and the Variance component methods. Actually, this is a mistitle because we really should talk about regression-based methods and the maximum likelihood methods, because the Haseman-Elston, if you think about it, is a variance component method. That's exactly what it is. But everybody talks about Haseman-Elston and the variance component method. When they say variance component, they mean the maximum likelihood method. So it's unfortunate. People are very bad about their terminology. But you've got to remember the Haseman-Elston method does look at variance components. That's what we've been looking at. Okay. The Haseman-Elston, excuse me, I'm going to put, whoops. Oh, I've got to turn. Well, I meant to turn that voicemail down. I'm sorry. Got that out. So the Haseman-Elston is robust to non-normality, and it's asymptotically equivalent in power if you use the W4 method. And it's much easier to compute. The variance component, so-called variance component or likelihood method, is powerful, not robust to non-normality, and it's difficult computationally. So that's the difference. They're both variance component methods. This is a regression method, and this is a likelihood method. And that's basically the difference. I leave it to you, whichever you want to do. If you want to use this method, you have to find, I suppose it's Chris Amos has some software that does this. Now, any other questions? Because we're slowly coming to the end of this session, I think. All right, let's see what's next. Essentially, they all model the covariance. That's what they do, the covariance of X1 and X2. That's exactly what they're all doing, that either by maximum likelihood or by some method of moments, if you like, because that's what the regression method is largely. All right, now we're going to talk about maximum likelihood analysis of affected relative pairs. This is Jane Olsen's baby, and she used to present this. I find it very difficult to follow these slides. We can take a little time over it, but I find it very difficult myself. So let R be the relationship between two affected individuals. Remember, this is affected relative pairs, so you're going to have a relationship between the two. Let IM be the marker information. Let A1 be the first relative affected and A2 the second relative affected. Now, you can go through and do all this stuff. You can think about it. It turns out I have been through it and I agree with it. You can get these probabilities, okay? And you get this, and you basically get a joint probability here, and then you split it up, and then you get this and you get this. The problem with this is that you don't really use these equations until a slide or two later. At that point, you've forgotten all this stuff. So I'll leave this with you. You can try and make sure you understand the logic here. And we are going to substitute these, I think it's in a couple of slides' time. Assuming linkage equilibrium, we want to the likelihood for the information, the marker information, given that A1 and A2 are both affected under two scenarios. You want it when the trait locus is the marker locus, that's complete linkage, and you want to contrast it for when the trait locus and the marker locus are unlinked, independent. That's what you want to do. Okay, let's say I'm not going to try. We will be using all these expressions in a minute, and then you'll see things cancel out. So under complete linkage, you have this. Under independence, you have this. And for this pair, what you want is the ratio of these two probabilities. You see, you've got here, you not only know the relationship, but the information from the markers. Here you have purely the relationship. So that's what you're doing. You're saying you're finding a probability, and these two are going to be the same, of course. That's not true what I said. Not these two, but you'll see in a minute. But basically, you're getting the likelihood or probability given the relationship and the marker information versus just the relationship. And then turns out you have this, and these probabilities cancel out. You get them from what we had before. And you end up with this. So to cut a long story short, because I'm not going to go through all this, to cut it very short, and you can try it and go through the algebra. This ends up here. And what we have here is we are using the relative recurrence risks. For unrelated, it's 1. The relative recurrence risk for parent offspring is L1, and the relative recurrence risk for mesozygotic twins is L2. We utilize those and we sum over the three possibilities. Here we have the probabilities of 1, 2, and 3 alleles identical by descent based on the relationship only. Here it is estimated at the marker location. That's the whole point. And so you have, for this J-SIB pair, you have ZI, which is just a log score, and it's log to base 10 of this ratio. So that's all this is. And remember that this is basically as a function of the recurrence risks. The relative recurrence risks. Okay, so that's the long and short of it. Now, let ZI be this for the Jth pair. We have lots of pairs of relatives, affected relative pairs. This is it for the Jth pair. And if we have n independent affected relative pairs, the total log score is just the sum of these. Now, I am sure if Jane Olsen was still alive, she would do something about this assumption of independent relative pairs. That's why I don't particularly like this method, this assumption, which is always made and is probably never true, or maybe partially true for if you have SIB pairs only. I mean, you may have independent SIB pairs, but she's going to include not only SIB pairs, she's going to do avuncular pairs, and I think grandparent-grandchild pairs, and half avuncular. I think we mentioned on day 1 all the pairs that we pull out. And I am so, this assumption of independence just doesn't go well for me. And in fact, I think we know enough now, maybe some of the work that Yun Ju has done can't remember, Yunju, whether you've published it or not yet, but we know something about how to allow for these non-independent pairs. I'm not sure whether what you did, Yunju, I can't remember whether you published it or not, and B, I can't remember whether it would work for this or not, but I leave that to you. Okay. So what we do is here, we set lambda 0 equal to 1 and maximize over lambda 1 and lambda 2. And note that lambda 2 cannot be estimated from unilinear relatives because for them, this is always 0. If they're unilinear, they can never have two alleles identical by descent. However, and this is another Jane Olsen bit, she reparameterizes these recurrence risks in this form here. So let us do the next thing. So we have 3 parameterizations of the model for affected SIB pairs. And here they are. Whoops, come back. The number of alleles identical by descent can be 0, 1, or 2. The original parameterization, I think that Neil Risch used was Z0, Z1, and Z2. And you can put them in this in terms of relative recurrence, these recurrence probabilities. And she puts them in the logistic form like this with a beta 1 and a beta 2. The sibling relative recurrence risk is just this on this scale here, and that's a quarter plus half the recurrence risk for if they share one allele identical by descent, plus a quarter, half for one allele and a quarter for 2. So that's it. Gets very complicated. Oh, we got a break right now. What is the time? It's probably nowhere near time. I can't see. Let me see what I've got. It's now, doesn't want to tell me.
2:17.
Oh, I see. I've got this thing upside, 2:17. And we are breaking until 2:50. So there's lots of times for questions. Yunju, let me ask you, do you think that the work you did would allow one to let these pairs be correlated? I can't remember exactly what you, and did you ever publish that paper in general? I can't remember.
No, I didn't publish it. It was my thesis.
I know it was. I know it was. But do you think it would work for this? I can't remember.
I mean, I did for the not for the likelihood ratio test, the framework, but for the score test frameworks. So
okay, but it probably would work in this framework too. Probably.
I think so. I guess for the
because I'll tell you why I think it would work is because these are just, this is just I think these are just functions of the likelihood ratio, bits and pieces. So I think it would work, but you never published it, so it doesn't matter, right? There's
I mean, I guess one of the reason that I haven't published it is because that, the way that I did is by finding the way to adjust for the non-independence of a affected related pair, but it was by the simulating the many different the pedigree structures. So, and also another complexity is that the covariates. So I mean, it will work for the cases that I did the simulation study, but I was not sure it will work for the in general.
And this is, as we'll see when we come back, this allows for one covariate, which Jane thought was very important, and she certainly had one example where it made a big difference. I think that's the data where we had the Gleason score for affected pairs with for prostate cancer. So, yeah.
Yes, that was the Goddard et al. The prostate cancer paper using the Whitmore and 2 one parameter model.
Right.
That's correct. The real problem is, though, it's a problem because it does make that assumption that you have independent, and I'm sure that if Jane were still alive, she would have found a way to correct that, similar to the way Yunju
Right.
her dissertation, which she tells me now she's never published. Oh well, I can't remember.
Well, you know, it may be timely to get some of your students to work on it again, Yunju, because of course, linkage studies have become popular again. And, you know, I had talked with Jane about this. I know you had too, Robert,
Right.
because this approach really is something that I was using a lot on my big extended pedigrees. But of course,
Right.
we knew the results weren't exactly right, because then in a big extended pedigree with many affecteds, you have a lot of non-independent pairs.
Exactly. Yeah.
And that's the power of those pedigrees. You don't want to take only one pair out of each of your pedigrees.
That's right.
And so I know she was interested in working on it. It was
I'm sure she would.
Tragedy when we lost her. Yeah.
Right. In her 50s. Right. I remember early 50s.
Yeah, she was so young.
Yeah.
But one of the things is, you know, it affected relative pairs in a non-parametric framework like this really is something that we need better approaches for.
Yeah.
You know, you can do some of that in Gene Hunter and Merlin,
right?
But there are real limitations to the pedigree size. And so when you get to a really big informative pedigree, those approaches don't work. They die, and you have to trim your pedigree, and you end up losing information content.
Yeah,
which
you see,
that was the benefit of this.
Yeah, and it would, you know, probably going up to great avuncular pairs out of huge pedigrees. And if this was probably a great idea, it was a great idea, but we never allowed for the non-independence, and that was sad. There's also a problem with the coverts, which we'll talk about after the break. But you know, there again, I wish to remind everybody, if they wish to go to the S.A.G.E open source, they can do what they want. They can make additions, make subtractions. And if you do, as a courtesy, you might want to let me know, but I'm out of it now. I'm sorry, I'm old. So anyway.
I have one idea or something that I have thought about it after I was done with my dissertation, is that, you know, it has to do with the complexity of like a pedigree structure itself. There isn't any general ways to adjust for that pedigree, you know, structure. But one thing that I was thinking, maybe is there any way to actually find or calculate or estimate some like a pedigree, like a information content that depends on the pedigree structure? You know what I mean? Some general way to like estimate the
well, you know, the other thing is
that to actually adjust for
the other thing is you could just assume they're independent and then use some kind of permutation test. I don't know how that might be very time consuming. I don't know, but that's another possibility. But the ideal would be to somehow allow for the non-independence in some way or other. Yeah.
Just like the CPL does have the ways to adjust for like a pairwise independence,
right,
pairs within SIPs. So that's the same kind of method, like you know, the ways that we can do within pedigree. You know what I mean? With the different types of like the pairs that the pedigree has. So yes, I guess it's kind of possible, but I guess I have to think more.
I don't know. And as I say, I'm getting a little bit old these days. So I don't know that I shall do anything more about it. Oh, I want to say to everybody, we were talking, because when we were talking about comparing two completely different models, we were talking about the Leibniz, Kolmogorov-Leibniz measure, and I said I said I'd seen one that was symmetric. It didn't matter which was the null hypothesis and which was the alternative. Well, since then, Yunju has found two, one unpublished and one published a long, long time ago, which to me, if I read the Ginsberg book and I saw what he was doing, I would substitute one of those for his method of choosing between two completely different models. That's what I would do. I don't think they're difficult as far as I'm sorry, I haven't read the papers in detail yet, but I don't think they're any more difficult to do. At most, I think the computation would just be twice as long. That's at most. Because it's like you do everything. I mean, one of those I saw, you do everything one way, then you do it the other way, and you sort of average in some kind of sense. That's what I remember. But I said the paper I saw was only maybe, I don't know, 4 or 5 years ago. And Yunju found one unpublished yet, and one that goes back to, I forget when, 1990 or something, something like that, very early paper, which I didn't even know existed. So, but I think a lot of these possibilities, you know, we have tests that we know have problems in that they make assumptions which we don't like. So it makes a lot of sense to do more not simulation, to use you know, get probability, get p-values from Monte Carlo approaches, and it makes a lot of sense to try and make these models that aren't quite right, make them a little bit better one way or another. And I mean, that's what, if I were still working on this, this is what I would be doing, I'm sure, but I'm not. Okay, so it is now 2:30 nearly. So we come back at 3 o'clock, right? Yeah.
Yeah.
You have half an hour break. Okay. And if you have any other questions, you can bring them back and we'll try. We'll continue with this for a little bit and other things. Okay. I'm not going to, I'll tell you what I will do. I will go on to the next slide. Break. And there we are. And I won't touch anything. I won't look at my email, and hopefully it'll work when we get back. Okay. Thank you, everybody. See you in what, half an hour, about something like that. Okay, good. I think